Hello students, welcome to EPG Pathshala. I am Dr. Aditya Saxena from the Department of Physics, Central University of Haryana. Today we are going to discuss about a module, properties of operators, commutators and identities under the paper Quantum Mechanics 1. So students, let us first see what all we are going to be learning in this module. Firstly, we'll know the important identities of commutator algebra. And it's important to know these identities because by using these identities, we can actually greatly solve the formalism of quantum mechanics. From here, we'll move on to learning the definitions of functions of an operator, and we will also study a few examples. We'll then get to know the differentiation of an operator and learn some properties relating to the differentiation of the operator. Then we will learn the definition of trace of an operator and study some examples. And it's also important to know the trace of an operator because if the trace is actually the sum of all the diagonal elements, and in case if we diagonalize a matrix, then simply by finding out the trace of the operator, we can actually find out the sum of all the elements of that matrix. Then we will learn the meaning of invariance of trace of the operator. And finally, we will study the example of a potential as an operator, including a useful identity. So, in this module, some important properties of operators and their commutators and some well-known identities are recapitulated. In particular, the definition of a function of operator, differentiation and trace of the operator with some examples are discussed. In this, we will also see how the differentiation of an operator actually tells us that if we are looking at two operators like the coordinate or the position operator and the momentum operator, then we can see when we move from the coordinate representation to the momentum representation, then the corresponding operators simply are the Fourier transform of the operator in the other representation. So, in case of position coordinates, the corresponding Fourier transform leads us to the momentum formalism or the momentum coordinate system, and vice versa. Then we will discuss the concept of the invariance of trace, and the purpose here is not only to acquaint you with the elementary properties of the operators, but also to familiarize you with some of the important identities which you will find useful in your subsequent studies in quantum mechanics. Commutator algebra and identities. It is useful differentiating the operators, a few simple identities of the what will happen when we differentiate the product of two operators operator in F the quantum mechanical formalism with respect to a variable t easily verified. D by dt the first such identity operator F in the commutator algebra is, and this is equal to of operator A operator F by dt operator B times plus operator G is equal to operator F times operator A by operator B of operator G. In order to prove this relation of operator let us write with operator or rather C. Let us consider, and we can see two vectors that this UI is and uj proved, and then write the following the commutator relation bra vector ui operators simply proceed F operators G to solve that commutator relation uj is equal to summation over commutator relation bra vector ui operator the next F, identity is ket vector uk commutator relation bra vector uk of operator A G times ket vector B uj with so operator we C can write is equal to commutator relation
write of operator
bra
A
vector
with
ui
operator C
d by dt
times of operator B
product of
plus
operator f
operator A
G
times commutator
vector
relation
uj
of
is
operator
equal
B
to
with
summation
operator
over
C.
k
And
bracket
if we
open
look at the
bra vector
right hand side
ui
of this equation
d
and
by
we open
dt
up,
of operator
we
f
will see that we
get
will
vector
finally
uk
reach the result
bra
that is
vector
written on
uk
the left hand side
operator
of the
g
equation.
get vector uj
Third identity
plus bra
commutator
vector
relation
ui operator
of
f get vector
operator
uk
A,
bra vector
commutator
uk
relation
d by dt
of
of operator
three
g
terms,
get vector
the
uj
first term being
bracket closed.
commutator
This relation we have written
of operator
after
A
substituting
with
for
the
the product
commutator
of f and
relation
g
of
d by
operator
dt
B
of
and
f and
operator
g
C
operator,
plus
and now we get
commutator
the final
relation
result as
of operator
bra vector
C
ui
with the commutator
d by
relation
dt of
of
product of
operator A
operator f and
with
operator
operator
g
B
get vector uj is
plus
equal to
commutator
bra vector
relation
ui
of operator
d by
B
dt
with
operator f
commutator
times
relation
operator
of
g
operator C
get vector
with
uj
operator A
plus
whole within
bra vector
brackets is
ui
equal to 0.
operator
So
f
if
times
we
d by
open up
dt
each of the
operator
three
g
terms on the
get
left hand
vector
side
uj
within
as
brackets
the last
and solve for
expression
the
is
commutator
valid
relation,
for
we
all
will
I
see
and
that
j,
all the
the
terms
relation is
cancel out.
established.
So
For
in this manner,
example,
we see that the
differentiating
commutator
a function
relation
e to the
is
power
cyclical.
operator a times
Now,
t
if
e to the power
operator
operator
A
b times
and
t,
operator
we
B are two
will proceed
operators
as
which
follows.
both commute with their commutator, that is, commutator of operator A and operator B, then we can try and verify two identities. A, commutator of operator A with operator B to the power n is equal to n times operator B to the power n minus 1 times commutator of operator A with operator B. And second, commutator of operator A to the power n with operator B is equal to n times commutator is equal to n times operator A to the power n minus 1 times commutator of operator A and operator B. Now, if we try and verify the first of these two relations, for n is equal to 2, we can write equation A as commutator of operator A with operator B whole square is equal to operator A times operator B square minus operator B square times operator A. And this is equal to commutator of operator A with operator B times operator B plus operator B operator A operator B minus operator B times commutator of operator B with operator A minus operator B operator A operator B, and this is equal to, after solving, commutator of operator A with operator B times operator B plus commutator of operator B plus operator B times commutator of operator A with operator B, and this is equal to twice of operator B times commutator of operator A and operator B. Commutator algebra and identities. It is useful
Differentiating
to
the
write
operators.
a few simple
Now let us
identities
see
of the
what
commutator algebra, which will be used extensively in the quantum mechanical formalism and which are easily verified. So the first such identity in the commutator algebra is commutator of operator A with operator B plus C is equal to commutator of operator A with operator B plus commutator of operator A with operator C. And we can see that this is proved if we open up the commutator relation on the left hand side and simply proceed to solve that commutator relation, we will reach the commutator relation on the right hand side. The next identity is commutator relation of operator A times operator B with operator C is equal to commutator relation of operator A with operator C times operator B plus operator A times commutator relation of operator B with operator C. And if we look at the right hand side of this equation and we open up, we will see that we will finally reach the result that is written on the left hand side of the equation. Third identity, commutator relation of operator A, commutator relation of three terms, the first term being commutator relation of operator A with the commutator relation of operator B and operator C, plus commutator relation of operator C with the commutator relation of operator A with operator B, plus commutator relation of operator B with commutator relation of operator C with operator A, whole within brackets is equal to 0. So if we open up each of the three terms on the left hand side within brackets and solve for the commutator relation, we will see that all the terms cancel out. So in this manner, we see that the commutator relation is cyclical. Now, if operator A and operator B are two operators which both commute with their commutator, that is, commutator of operator A and operator B, then we can try and verify two identities: A, commutator of operator A with operator B to the power n is equal to n times operator B to the power n minus 1 times commutator of operator A with operator B, and second, commutator of operator A to the power n with operator B is equal to n times commutator is equal to n times operator A to the power n minus 1 times commutator of operator A and operator B. Now, if we try and verify the first of these two relations, for n is equal to 2, we can write equation A as commutator of operator A with operator B whole square is equal to operator A times operator B square minus operator B square times operator A, and this is equal to commutator of operator A with operator B times operator B plus operator B operator A operator B minus operator B times commutator of operator B with operator A minus operator B operator A operator B, and this is equal to, after solving, commutator of operator A with operator B times operator B plus commutator of operator B plus operator B times commutator of operator A with operator B, and this is equal to twice of operator B times commutator of operator A and operator B. Functions of operators. If a function f of a variable z is defined by a series, then by definition the function of the operator A is the operator f as a function of operator A, and this is defined by the series f as a function of A is equal to summation n going from 0 to infinity Cn operator A to the power n, where Cn are the coefficients. The most important function defined in such a manner by the series is the exponential function, where the exponential function of operator A is defined as exponential function of operator A is equal to summation over n going from 0 to infinity operator A to the power n upon n factorial, and this is equal to operator 1 plus operator A plus operator A square by 2 factorial plus so on plus operator A to the power n upon n factorial. It is also easy to check if operator A is Hermitian or not. So, if we have an operator in the form of a series of operator A, then further we can write f as a function of operator B, operator A, operator B inverse is equal to operator B times f as a function of operator A times operator B inverse, and this identity can easily be checked by expanding the function in series. In particular, for a unitary operator U, we have a useful relation f as a function of operator U, operator A, operator U dagger is equal to operator u times f as a function of operator a, operator u dagger. And for understanding this identity or relation, we can take an example. So if we have an eigenvector given by ket vector phi a of the operator a, such that we can write operator a acting on ket vector phi a is equal to a times ket vector phi a, where a is the eigenvalue, then applying the operator n times, that is operator a to the power n acting on ket vector phi a is equal to a to the power n times ket vector phi a. Thus, f as a function of operator a acting on ket vector phi a is equal to summation over n going from 0 to infinity c n times a to the power n ket vector phi a, and this is equal to fa acting on ket vector phi a. Functions of operators. So from our previous relation, we can see that it follows that if we have an eigenvector ket vector phi a of the operator a with eigenvalues a, then this is also the eigenvector of the function of f of operator a with the eigenvalue fa. For this, we can consider an example. Let us take a matrix OZ is equal to 1, 0, 0, minus 1, which is a 2 cross 2 matrix. Then exponential of the matrix OZ, which is equal to e to the power OZ, is given as a matrix which is again a 2 by 2 matrix of the form e 0, 0, e to the power minus 1. Now, the functions containing two or more operators, in such cases, we have to keep in mind the order in which they are appearing. That means it is important for us to remember the order in which the functions are appearing or acting. And again, to understand this, let us take an example. The operator e to the power operator a, e to the power operator b, comma, e to the power operator b, e to the power operator a, and e to the power operator a plus operator b are, in general, not equal. It is only when the operators a and b commute, that is, commutator of operator a with operator b is equal to 0, is when the three cases discussed above are equal, that is, e to the power operator a, e to the power operator b is equal to e to the power operator b, e to the power operator a is equal to e to the power operator a plus operator b. Differentiating the operators. Now let us see what will happen when we differentiate the product of two operators, operator f and operator g, with respect to a variable t, that is d by dt of operator f times operator g, and this is equal to d operator f by dt times operator g plus operator f times d by dt of operator g. In order to prove this relation, let us write, or rather let us consider two vectors ui and uj and then write the following equation. Bra vector ui operators f operators g ket vector uj is equal to summation over k bra vector ui operator f ket vector uk bra vector uk operator g ket vector uj. So we can write ui, so we can write bra vector ui d by dt of product of operator f operator g ket vector uj is equal to summation over k bracket open bra vector ui d by dt of operator f ket vector uk bra vector uk operator g ket vector uj plus bra vector ui operator f ket vector uk bra vector uk d by dt of operator g ket vector uj bracket closed. This relation we have written after substituting for the product of f and g, d by dt of f and g operator, and now we get the final result as bra vector ui d by dt of product of operator f and operator g, ket vector uj is equal to bra vector ui d by dt operator f times operator g, ket vector uj plus bra vector ui operator f times d by dt operator g, ket vector uj. As the last expression is valid for all I and j, the relation is established. For example, differentiating a function e to the power operator a times t, e to the power operator b times t, we will proceed as follows. Useful identities. Now, for example, if we want to differentiate a function, then let us consider the following case. Differentiating a function e to the power operator a times t, e to the power operator b times t, we will proceed as follows. We write this as d by dt within brackets e to the power operator a times t, e to the power operator b times t is equal to operator a e to the power operator a times t, e to the power operator b times t plus e to the power operator a times t operator b e to the power operator b times t, and this is equal to e to the power operator a times t operator a e to the power operator b times t plus e to the power operator a times t operator b e to the power operator b times t, and this is equal to e to the power operator a times t operator a e to the power operator b times t plus e to the power operator a times t e to the power operator b times t operator b, but not as operators a plus b within brackets e to the power operator a times t e to the power operator b times t. That means that the order of the operators is important. Now let us see how we can prove the relation e to the power operator a times operator b times e to the power minus operator a, where this is given by the relation operator b plus commutator of operator a and operator b plus 1 by 2 factorial commutator of operator a with commutator of operator a and operator b plus 1 by 3 factorial commutator of operator a with commutator of operator a with commutator of operator a and operator b plus so on. Useful identities. Now, in order to prove the relation mentioned above, let us consider the expression f as a function of lambda, which is given by e to the power lambda times operator a, operator b, e to the power minus lambda times operator a. Now, using the Taylor series expansion for the function f as defined above, we write f lambda or f of lambda is equal to f of lambda equal to 0 plus lambda times df by d lambda at lambda equal to 0 plus lambda square upon 2 factorial d2 by d lambda 2 of f at lambda equal to 0 plus so on. Now differentiating this above expansion with respect to f of lambda, that is, and calculating the function at lambda equal to 0, we get f of lambda equal to 1 is equal to e to the power operator a times operator b times e to the power minus operator a, and this is equal to operator b plus commutator of operator a and operator b plus 1 by 2 factorial commutator of operator a with the commutator of operator a and operator b plus so on, and this proves the identity that we have defined above. Now similarly, we can also prove the corollary for the above relation, that is, if we have two operators a and b which commute with each other and also with their commutator, that is, operator a and b commute with their commutator of operator a and operator b, then e to the power operator a e to the power operator b is equal to e to the power operator a plus operator b plus 1 by 2 times commutator of operator a with operator b, and the students are advised to work this out and see whether this identity can be proved.
Trace of an operator. Trace of an operator is the sum of its diagonal matrix elements and is denoted by TR operator A. Trace of an operator. For a discrete orthonormal basis given by ket vector ui in the vector space, by definition, the trace is given as trace of operator A is equal to summation over I ui ket bra vector operator A ui ket vector, whereas in case of a continuous orthonormal basis ket vector u alpha, it is defined as trace of operator A is equal to integration over d alpha bra vector u alpha operator A ket vector u alpha. Now let us look at the invariance of trace. The sum of the diagonal elements of the matrix representing an operator is independent of its basis chosen. To show this property, let us consider the case of a change from discrete orthonormal basis to an other discrete orthonormal basis. That means we're going to be changing from one discrete orthonormal basis to another discrete orthonormal basis. Mathematically, this can be written as summation over I bra vector ui operator A ket vector ui is equal to summation over I bra vector ui bracket open summation over k ket vector wk bra vector wk bracket closed operator A ket vector ui. So again discussing the invariance of trace, we can rewrite the equation given earlier, and the right hand side of the equation can then be written as summation over I k bra vector ui ket vector wk bra vector wk operator A ket vector ui, which is equal to summation over I and k bra vector wk operator A ket vector ui bra vector ui ket vector wk. Note that it is always possible to change the numbers in the product. So using this closure relation or the closure property, we get summation over I bra vector ui operator A ket vector ui is equal to summation over k bra vector wk operator A ket vector wk. And using this relation, the following important properties regarding the trace of the product of two or more operators are worth recording. The first property is trace of operator A and operator B is equal to trace of operator B and operator A. That means that the trace of the product of the operators remains unchanged when there is an interchange of the order in which the operators are operating. And the second property is trace of the operators A, operator B and operator C. That is, the trace of the product of the operators A, B and C is equal to trace of the product of the operators B, C and A, and this is equal to trace of the product of the operators C, A and B. That means the trace of the product of three operators remains invariant in cyclical change or cyclical transformation or interchange. Now let us prove the first property that we had written above. So let us write down the trace of the product of operator A and operator B, and this is given by summation over I bra vector ui operator A operator B ket vector ui, and this is equal to summation over ij bra vector ui operator A, ket vector uj, bra vector uj, operator B, ket vector ui. And this is equal to summation over ij, bra vector uj, operator B, ket vector ui, bra vector ui, operator A, ket vector uj. And this is equal to summation over j, bra vector uj, operator B, operator A, and ket vector uj. And this is equal to the trace of the product of the operators B and A. An important example. Now let us consider a particle of mass m in a one-dimensional problem described by a Hamiltonian operator h given by operator h is equal to operator p squared by 2m plus operator v, where the first term is on the right hand side is the kinetic energy term or the kinetic energy operator, and the second term on the right hand side is the potential energy operator, and where the eigenvectors of the Hamiltonian operator h are denoted by ket vector phi k, so that Hamiltonian operator h acting on ket vector phi k is equal to ek times ket vector phi k, where ek is the total energy eigenvalue corresponding to the above mentioned Hamiltonian operator. Now we can derive the identity, which is defined as follows: summation over s within brackets es minus ek modulus whole square of x ks is equal to h cross square by 2m, where h cross is equal to h by 2 pi and h is the Planck's constant, and xks denotes the matrix elements bra vector s, operator x, ket vector k. So in order to prove this identity, let us start from the commutator half commutator of x and h with operator x is equal to operator x, operator h, operator x minus half operator h, operator x square minus half operator x square, operator h. Now let us calculate the matrix elements of the terms on the right hand side. So we can write half bra vector k commutator of x and h with operator x, ket vector k is equal to bra vector k, operator x, operator h, operator x, ket vector k minus half ket bra vector k, operator h, operator x square, ket vector k minus half bra vector k, operator x whole square, operator h, ket vector k. An important identity. Now from the above equation, let us consider the first term on the right hand side. Bra vector k, operator x, operator h, operator x, ket vector k is equal to summation over s and t, bra vector k, operator x, ket vector s, bra vector s, operator h, ket vector t, bra vector t, operator x, ket vector k, and this is equal to summation over s and t, bra vector k, operator x, ket vector s, es delta st, bra vector t, operator x, ket vector k, and this is equal to summation over s, bra vector k, operator s, ket vector s, es, bra vector s, operator x, ket vector k, and this is equal to summation over s, es modulus whole square of x ks. Proceeding in a similar manner, the last two terms can also be simplified, giving half bra vector k commutator of operator x, operator h with operator x, ket vector k is equal to summation over s within brackets es minus ek modulus whole square of x ks. Now if we substitute for the Hamiltonian operator h with operator h naught plus operator v on the left hand side of the matrix element, where we define operator h naught is equal to operator p square by 2m
Then we get bra vector k within brackets commutator of operator x and operator h plus operator v with operator x ket vector k, a useful identity. So looking from the above equation, if we have the basis representation of the basis vectors ket vector x, in which we calculate the expectation value, the commutator of operator x operator v is equal to 0. Thus, we finally have commutator of operator x and operator h naught with operator x, where operator h naught is equal to operator p square by 2m. Now, commutator of operator x and operator p square by 2m is equal to 1 by 2m I h cross 2 times operator px, and commutator of operator px with operator x is equal to minus I h cross. So substituting these results above, we get on the left hand side half bra vector k commutator of operator x operator h naught with operator x ket vector k is equal to half h cross square by m. This identity is called the Thomas-Rishi-Kuhn sum rule, which will be found useful in the future studies that we undertake in the formalism of quantum mechanics. So students, now let us round up what all we have learned in this module. So firstly, we learned the important identities of commutator algebra, which we will be using very frequently and very exhaustively in our formalism of quantum mechanics. Then we learned the definition of function of an operator, and we also studied a few examples of the function of an operator and how these work. Then we learned the differentiation of an operator, and also we learned some of the properties of the differentiation of an operator. Then we learned the definition of trace of an operator, and we also studied some of the examples of the trace of an operator. And we also learned how to find out the trace of an operator, where the trace of an operator is just the sum of the diagonal elements of the matrix. Then we learned the meaning of invariance of trace of an operator, and finally we studied the example of a potential as an operator, including the useful identities that are associated with the potential as an operator. Thank you.